Welcome back to the Deep Dive. Today we are unpacking a reality that feels like it's been slowly creeping up on us for the last few years, and now here in 2026, it's impossible to ignore. We're looking at the absolute dirty secret of artificial intelligence.
It's the elephant in the server room, isn't it? For so long, the whole conversation was about intelligence. How smart can the models get? Can they write poetry?
Right. Can they code better than a senior developer?
Exactly. But we sort of ignored the physical cost of all that intelligence.
We really did. We treated AI like it was magic, just this ethereal code floating in the cloud somewhere, totally disconnected from the laws of physics. But today, we're grounding that magic.
We have to.
Yeah, and we're basing this deep dive on a really compelling article by Johan Steyn. It's called Neuromorphic Computing, the energy-efficient counterpunch to AI hunger.
A great title.
It is, and honestly, the picture he paints of our current landscape is, well, it's resource-intensive, to put it mildly.
That is definitely putting it mildly. I mean, if you look at the energy reports from just the last 12 months, the narrative has shifted so violently. It used to be all about scale at all costs.
Scale at all costs.
And now the constraint isn't silicon anymore, it's electricity.
And Steyn actually points to a Reuters report from late 2025 that I think just perfectly encapsulates this moment. It highlighted that big tech is actively pivoting back to gas and nuclear energy.
Just to keep the lights on for their data centers.
Exactly.
Right, and just think about the irony of that for a second. We have the most futuristic technology imaginable, AI, and it's forcing us to resurrect 20th century energy strategies just to keep the servers from going dark.
Because the grid just can't keep up.
The grid is struggling. I mean, data centers are now competing for power like it's a finite raw material.
Because it is.
Because effectively it is. We're seeing these massive interconnection queues, huge political pressure on utilities, and, corporate boards are suddenly becoming experts on energy policy.
Yeah, the physical layer of tech is biting back hard.
It is.
Which brings us to our mission for today. We're exploring the potential solution to this energy deadlock. A technology that Steyn calls the counterpunch. We're talking about neuromorphic computing.
It's a term that sounds incredibly sci-fi, almost cyberpunk, but at its core, it's just biomimicry. It's about building computers that think and consume energy more like a human brain.
And less like a calculator.
A lot less like a calculator.
And that's the question we need to answer for you today. Is this just another buzzword, something to slap on a pitch deck to get VC funding? Or is this a real architectural shift that could actually save us from an energy crisis?
And to answer that, we really have to look under the hood. We need to understand why our current computers are so hungry in the first place, and then how a brain-inspired chip changes the fundamental physics of computing.
Okay, so let's start with the problem. Why is the current way we do computing, the architecture we've been using for decades, so inefficient? Steyn talks about the brute force nature of it.
To get the inefficiency, you have to visualize how a standard computer chip works. It's built on what's called the von Neumann architecture. It's incredibly powerful, obviously, but it's clock-driven.
Clock-driven.
Yep.
So everything happens to a beat, like a metronome.
Exactly. Imagine a massive factory assembly line. That conveyor belt moves at a very specific speed, tick, tick, tick.
Okay.
Every single workstation on that line has to check the belt every single time it moves, regardless of whether there's a part on it or not.
So even if the belt is completely empty, all the machines are running at full power.
Precisely. The circuits are synchronized. They are switching and checking millions, sometimes billions of times a second. It's like keeping your car engine revving at 5,000 RPM while you're sitting at a red light.
Just in case you need to move.
Just in case. It's constant consumption for potential work.
That sounds incredibly wasteful when you put it like that. And I'm guessing the brain doesn't work that way.
Not even close. I mean, the human brain is the most efficient computer in the known universe. It's handling language, complex pattern recognition, motor control, memory, emotions, all at the same time.
Right.
And do you know what the power budget is for all of that?
I have heard this stat before, and it always just blows my mind. It's something like 20 watts.
Roughly 20 watts. That's barely enough to power a dim light bulb. If you tried to simulate what the human brain does with standard GPU hardware, the stuff running our AI models right now, you'd need a small hydroelectric dam to power it.
A whole dam.
Ah.
So how does the brain cheat the physics? How does it do so much with just a couple of watts?
It uses an architecture that is event-driven.
Yeah.
Or sparse.
Sparse. That feels like a key word here. Let's unpack that.
Okay, think about it this way. If you're sitting in a quiet room, just staring at a white wall, Your brain isn't constantly reprocessing every single pixel of that wall every millisecond.
It's not screaming white wall, white wall, white wall at me.
Exactly. It's effectively idling. It's in a low energy state. But if a fly were to land on that wall boom,
That's an event.
that's an event. The specific neurons associated with that part of your visual field fire, they spike.
A spike.
Yes. And in neuromorphic computing, we call these spiking neural networks, or SNNs. Information is only processed when something changes. If there's no new data, there is basically no power consumption.
So going back to the car analogy, this is a car that shuts its engine off completely when you stop, and then instantly fires just the necessary cylinders the moment you touch the gas.
That's a really good way to visualize it. It eliminates that idle tax. But there's another massive source of waste in traditional computing that Steyn highlights, something he calls the data movement tax.
Oh, I love this term. It feels so relatable to anyone who's ever worked in a big organization. What exactly is being taxed here?
Energy and time. In that traditional von Neumann architecture we mentioned, the processor, the part that does the thinking, and the memory, the part that holds the data, are physically separate.
Okay, different components on the board.
Right. So every time the processor wants to do a calculation, it has to send a request over to the memory, fetch the data, bring it all the way back to the processor, do the math.
And then send the result all the way back to the memory.
Exactly.
It's like having a chef in the kitchen, but the refrigerator's in the building next door.
Yeah.
Every time they need an egg, they have to run outside.
That's a perfect analogy. And in modern computing, that run next door generates heat and consumes a ton of electricity. In fact, for a lot of AI workloads, we spend more energy just moving the data around than we do actually performing the calculation.
And that is the data movement tax.
Correct. And neuromorphic chips aim to basically abolish that tax. They use an architecture that's often called in-memory computing. They try to put the processing logic right next to or even inside the memory cells.
So the chef is now cooking inside the walk-in fridge.
Ideally, yes. The distance the data has to travel drops to near zero, and when that distance drops, power consumption just plummets.
It sounds so simple conceptually, but I imagine engineering that at a microscopic scale is unbelievably difficult.
It's incredibly hard.
But this is all fascinating theory, and Steyn's article suggests we are moving way past the theoretical stage. This isn't just paper research anymore. We are seeing actual hardware.
We are, and this is where the deep dive gets really interesting because we're seeing this global race to build these things. It's not just one company or one country.
Yeah, Steyn points to research coming out of MIT just recently, in late 2025.
Yes, they were working on stacking active components.
That's it.
Yeah, so they're physically stacking layers of transistors and memory right on top of each other to shrink that travel distance we just talked about.
It's a literal skyscraper of chips instead of a sprawling city.
Exactly. But maybe the most tangible example Steyn mentions is a machine called the BiExplorer 1.
The BiExplorer 1. This was reported by Tom's Hardware, and the description of this machine is just, it's striking.
It really is. It's a prototype coming out of China.
And visually, they describe it as being about the size of a mini fridge.
A mini fridge. But inside that box, you have 1,152 CPU cores.
Okay, so for context for our listeners, a high-end consumer desktop might have, what, 16, maybe 24 cores?
Right. So over 1,000 cores is serious server-grade territory. Usually a machine like that would be a rack-mounted beast screaming with cooling fans.
And needing a dedicated industrial power line.
Oh, yeah. 220-volt line, a specialized cooling room, the whole setup.
But the BiExplorer,
It runs on a standard household outlet.
wow, that is the counterpunch right there.
Exactly. It creates this whole new category of machine. It's not quite a supercomputer, but it is absolutely not a standard PC. It's a dedicated, brain-inspired AI server that you could, in theory, plug into your living room wall without blowing a fuse.
It just shows that the whole work per watt ratio is fundamentally shifting.
Massively.
And it's not just China. Steyn highlights that Europe is taking a very different, almost exotic approach to this.
Yes, the Innovation News Network reported on a European initiative focusing on LED-based neuromorphic computing.
LED-based, you mean?
Yeah.
Using light.
Photomics. So instead of using electrons moving through copper wires, which creates resistance and heat, they're using photons, light, to transmit information.
So speed of light computing.
Speed of light and theoretically almost zero heat from the data transmission itself. It's a completely different path to the same goal. Massive efficiency.
It shows we're in this period of like divergent innovation.
That's a great way to put it. We don't know which architecture will win yet, the stacked chips, the photonics, or something else, but everyone agrees that the current brute force method is a dead end.
So we have the theory acting like a brain, we have the prototypes, mini fridges, and light-based computers. But I think we need to manage expectations here for the listener. Steyn is very careful to point this out.
He is, and it's a crucial reality check.
So if I go to ChatGPT or a Gemini tomorrow, is it running on a neuromorphic brain?
No, and it probably won't be for a long time.
Why not? I mean, if it's so much more efficient, why isn't OpenAI or Google just switching everything over?
Because the current generation of large language models, the GPTs of the world, they're mathematically optimized for the old way of doing things. They rely on massive matrix multiplication, and traditional GPUs are actually incredibly good at that one specific task, as long as you can feed them enough electricity.
So neuromorphic isn't about replacing the big cloud brains immediately.
Not yet. Where Neuromorphic really shines right now isn't in the massive data center training a model. It shines at the edge.
The edge. This is a term that gets thrown around a lot in tech. Let's define it clearly for this context.
So the edge is basically anywhere that data is actually created that isn't a centralized server. It's the camera on a telephone pole,
The drone inspecting a crop field.
the wearable health monitor on your wrist, the sensor deep inside a factory machine.
All the devices out there in the wild.
Correct. And out in the wild, you don't have a direct line to a nuclear power plant. You have a battery. Or maybe a little solar panel.
And watts and heat are the enemy.
They are the enemy. And right now, most of those devices are dumb. They just collect data and send it to the cloud to be processed.
And that round trip, sending a video feed from a drone to a server in, say, Virginia, just to see if there's a crack in a pipeline, is slow and expensive.
And very energy intensive.
So how does a neuromorphic chip change that drone's life?
It allows the drone to process the data locally. Remember the spike concept.
Only working when things change.
Right. So imagine a security camera looking at an empty warehouse. A traditional AI camera is processing 30 frames every single second, burning power, sending data. A neuromorphic camera just sits there, effectively asleep, consuming microwatts of power.
Just waiting.
And then a shadow moves. Spike. The chip wakes up. It processes only the pixels that change. It identifies human. It sends one tiny text alert.
And then it goes back to sleep.
Back to sleep. The efficiency gain there is just astronomical, orders of magnitude. You're moving from needing a battery charge every day to maybe needing one every year.
It decouples intelligence from the power grid.
Perfectly said. It decouples them. And that decoupling leads us to a really powerful section of Steyn's article, focusing on the global south and specifically on South Africa.
Yes. I found this perspective incredibly grounding. Because we so often talk about AI from the perspective of, Silicon Valley or London.
Right, where historically we've just assumed that power is infinite and always on.
But Steyn points out that in places like South Africa or really large parts of the developing world, the grid is not a guarantee.
Not at all. The whole narrative that the cloud is always there, it just collapses when the lights go out. If your business relies on an AI that needs a constant, high-speed connection to a data center, and you have load shedding for 4 hours a day...
You don't have an AI system, you have a brick.
You have an expensive brick. So for these regions, energy efficiency isn't just a green initiative. It's not about ESG goals.
No. As Steyn puts it, it's a feasibility requirement.
Exactly. If the tech isn't efficient enough to run on local battery power or an unreliable grid, it simply cannot exist there.
That is such a powerful reframing of the problem. It shifts the whole conversation from saving the planet to just access to technology.
It does. Think about a clinic in a rural village using AI to diagnose X-rays. They can't upload those huge image files to the cloud over a spotty 3G connection.
No way.
They need a chip in the X-ray machine itself that can do the diagnosis right there on low power, regardless of whether the main grid is up.
So neuromorphic computing could actually be the key to democratizing AI.
Absolutely. It allows high-level intelligence to function in low-resource environments. And that is a massive deal for the Global South. It means they don't have to wait for the massive industrial power grid to catch up before they can use advanced tech.
This feels like it has huge implications for business leaders, too, no matter where they are. Steyn suggests a fundamental shift in our metrics.
Yes. For the last 10 years, really the only metric that mattered was accuracy.
Right. Is the model 98% accurate or 99% accurate?
And we'd chase that last percentage point at any cost. Steyn argues we're moving to a new metric, work per watt.
Work per watt.
If getting that extra 1% of accuracy requires 50% more energy, business leaders are finally starting to say, no thanks. It's becoming an ROI calculation.
Because that energy cost hits the bottom line directly.
It hits operational limits. If you're a CTO today, you need to be asking, what is driving my carbon footprint? What's driving my cloud bill?
Right. Is it necessary to send all this data to the cloud for a round trip, or can I just process it on the device with a low-power chip?
It's almost a return to the discipline of the old days of computing, where you had to be efficient because memory was expensive.
Now we have to be efficient because energy is expensive.
Precisely. Constraints breed innovation. And this is also becoming a massive issue for policymakers.
Steyn mentions this is now an industrial policy issue.
It has to be. Governments are looking at these projected energy demands for AI and realizing they don't have the power plants to support it. If AI starts to destabilize the national grid, the government will step in.
So efficiency becomes a matter of national competitiveness.
It does. It's not just about who has the smartest AI anymore. It's about who can run their AI without bankrupting their energy sector or compromising their grid stability. It's a strategic advantage to be energy independent with your compute.
Okay, but before we get too carried away with this utopian vision of efficient brain-like chips everywhere, Steyn does offer a pretty big reality check.
He does, and we should definitely heed it. He warns against the hype. He says, and I'm quoting here, hype will not keep the lights on.
So what are the bottlenecks? If the hardware exists like the Buy Explorer, why isn't it everywhere already?
It's the ecosystem. It's all the software. You can't just buy a brain chip and run your standard Python code on it.
Because the architecture is completely different.
It's fundamentally different. Developers are used to thinking in linear instructions. Do A, then do B, then do C. Neuromorphic requires you to think in spikes, in events, in parallelism.
So there's a massive reskilling that needs to happen.
A huge learning curve. And the supply chains need to mature. Procurement departments and big companies need to understand what they're even buying. You know, integrating a mini-fridge supercomputer into a legacy corporate IT network is not a plug-and-play scenario yet.
It's a transition period. It feels like we're trying to change the engine of the plane while it's in midair.
That is a great analogy. We can't stop using the old AI because it provides so much value today, but we have to start building the new infrastructure or we will literally run out of fuel.
So pulling this all together, we have an undeniable energy crisis, and it's being driven by our thirst for AI.
Right.
And we have a technology neuromorphic computing that mimics the brain's elegance to try and solve it. It's already showing up in real prototypes in China, Europe, and labs like MIT. And it's finding its first real home at the edge in drones, cameras, and sensors, where efficiency is basically survival.
That's the summary. It is a shift from brute force to elegance.
Elegance. Yeah, I really like that word in this context. It's not about building a bigger hammer. It's about learning how to hit the nail perfectly.
Precisely. Neuromorphic computing tackles the most under-discussed constraint of our time: energy. As Steyn concludes, if AI is becoming a utility, like water or electricity, then efficiency becomes a moral and economic obligation.
And that leads to a fascinating final thought for the future. We have spent the last few years totally obsessed with who has the smartest AI. The leaderboard is always about IQ.
But the game is changing.
Yeah, maybe the winner of the AI race isn't the company with the highest IQ model.
No. The winner might just be the one who can run their model without draining the grid, the one who can put intelligence into a solar-powered sensor in the middle of a desert and have it work reliably for 5 years without anyone touching it.
That's a different kind of supremacy.
It is.
It's resilience over raw power. It really makes you think about our own digital lives, doesn't it? We're so used to paying that data movement tax without even realizing it. Every time we upload a massive video file to the cloud, just to store it.
We're burning watts. We're contributing to the load.
It's definitely something to mull over. Next time you feel your phone heat up while it's doing a simple task, just think. Maybe it needs a little less silicon and a little more brain.
A little more spike, a little less crunch.
I like that. A little more spike, a little less crunch.
Yeah.
That might just be the tagline for the next decade of computing. Thank you so much for breaking all this down with us today.
My pleasure. It is going to be a fascinating field to watch evolve.
And thank you to our listeners for diving deep with us. We will catch you on the next one. Stay curious and watch your watts.